Welcome back. We're going to look at the physics chapters from the second half of the semester. And let's start off with motion. Frames of reference are used to observe relative motion or motion relative to something else. And remember, all motion is relative because even something that appears to not be moving, like the Earth, really is moving from a different perspective. Namely, if you were in space looking down, you would see that the Earth was rotating around an axis and circling the sun at the same time. So just remember that all motion is relative to something, and those somethings are frames of references. Which means if we want to know if something is moving, we need to choose a frame of reference that is not moving relative to that object. For example, choosing a sign or a tree or some other landmark on the ground outside of a moving car, as opposed to, say, another car traveling in the lane next to you. Because that's also moving, you wouldn't be able to accurately depict the speed from those vehicles. So, choose a reference frame not moving relative to that object. Relative motion, of course, is a change in position relative to our reference point. So, for example, a car moving past a signpost would be how we measure the speed of that car relative to the ground, which you know is what the cops are interested in are you obeying the speed limit, not your speed relative to their car. How we calculate speed is distance over time. And velocity and speed are very, very similar. Both are d over t. So speed equals d over t. V equals d over t. The distinction, which exists but is not very likely to be emphasized on the test because they do tend to use these terms nearly interchangeably, is that speed has no direction, velocity does. Because this d is technically distance, and this d is technically displacement. Practically speaking, if you're given a graph, a dt graph, a distance-time graph, they will confuse these two things. And you could have, let me use a different color here, two different slopes, one being positive and one being negative, and they're going to ask you what's the difference between these two. Or they could ask you what's the difference between these two. And you go, okay, well, this red guy is returning to start, or origin, whatever that happens to be that we've chosen, and this guy is moving away from the origin. At this point, they've crossed paths, so they haven't hit each other, they've just passed by each other, like two cars traveling in opposite directions. Now, the funny thing is, if this is a distance-time graph, technically this red line can't possibly exist because distance can never be negative. However, on state tests, I've never seen them actually do this, and instead, what they're really graphing, or trying to graph, is position versus time. And what this means is that this would be your negative velocity in red, this would be your positive velocity in black. But again, they usually don't say position versus time, they will just say distance versus time, expect you to know that the slope is speed, and then have a question that treats it as if it's velocity instead. So just be aware that those graphs don't always translate the way they're supposed to. And the reason for that is, in practice, these two graphs are almost always used to represent velocity, and this graph is not very useful in practical application, so we just usually call it distance when we're really talking about position. It's a technicality, and so most people just graph it as d versus t. But anyway, I digress. Speed is distance over time, so technically can't be negative because negative tells us direction, while velocity can be negative because it can tell us direction, it's vector. So speed also comes in two different flavors. There's the average speed versus the instantaneous speed. Now you can read this that I scanned in there. In case you couldn't see it, I just zoomed in on it. But I'm also going to show you what that means graphically. Zoom out there. So if I sketch another one of these DT graphs, distance versus time, which we're treating as position versus time, and I have two graphs. Let's start in black, and let's say the path that I travel looks something like this. Now we can say for our trip, and let's go ahead and break this up into time frames. We'll just number, or not number them, we'll letter them, A, B, and C. Interval A, I can tell is faster than interval C, because if I lay my pencil over it, I'll do two pencils so you can see the difference. One of them has a shallower slope, the red marker. And that's because in interval C, you're traveling slower than you are in interval D. You're covering less of the y-axis for each of the same interval on the x-axis. If you were traveling the same speed, these lines would be parallel to each other and would never touch. But we slowed down here, so the lines will intersect back here. The other thing you can tell is that you're not moving at all in interval B. What this graph is showing us, at any given point, if we looked at a speedometer, we could read, that one's hard to see, let me zoom in on that. At any given point, for example this x, you could look at your speedometer and know the instantaneous speed, say 50 miles an hour. And I can look at my speedometer at any of these x's along the A interval, and it would always show 50 miles per hour. Why? Because this is a constant speed. Well then, at B, if I do those same three x's at 3 points in time, it would always show 0 miles per hour, because it's not moving. And at interval C, same three x's, if I said these were 50 miles an hour, perhaps these are 40 miles an hour. And they will always show 40 miles per hour. Well, that would give us instantaneous speed at any particular point in time. It's the speedometer speed. But if you want to know, to make this journey in one continuous trip, how fast would I have to travel? I would connect my start and my end by a single line. Let's do it in blue. Now, because I haven't drawn this to scale, it overlaps with my other line here, just a little smidge. So, just bear in mind, this is not to scale. But what you can see is that the average speed is one continuous speed that would get me from point A to point B without stopping. And it's slower than my fastest speed. Okay. If I did my line trick again, I can see it's a shallow line. And it's actually faster than my slowest speed. But because I have this big resting interval here, the lines almost totally overlap right here. So blue line represents the average speed, or average velocity, if they ask it that way on a question. Whereas the red X's represent the instantaneous speed, or your speed at any given moment in time. And the easiest way to do this is if you're given a whole graph and they ask for the average speed, it's the total distance over the total time, d over t. Going back to that graph again for a second, what that would mean is I would want to read my final total distance traveled, whatever that is, divide it by my final total time, whatever that is. And that would be your average speed for the trip. Instantaneous speed you would have to calculate at each given point. So if they give you a point in time, you would have to calculate it for that particular point. Alright, moving right along. Velocity, we already sort of discussed position versus time instead of distance over time. but both are calculated as d over t. Acceleration is the change in velocity over the change in time. So I'm going to show you this equation real quickly. A equals delta v over delta t. The delta in front of the t is usually dropped, and they'll just say it takes 10 seconds, which is a change in time, instead of saying from 2 seconds to 12 seconds. They're not going to make you do that math. So we usually just drop this delta, and we're left with delta v over t. It is there, but we hide it. And so practically what this means is the change in velocity, final minus initial, what you wind up going at versus what you started at, divided by how long it takes you to get there. And acceleration is a change in velocity or speed over time, which means it has those weird looking units. Here's a velocity unit. If I change it over time, I'll change the direction of my fraction bar so it's easy to see. I have meters per second per second. Since they're the same unit, I can actually mathematically combine them. I'm not going to show you that. Just know that they do combine. Meters per second squared. They don't have to combine, though, so you can be left with meters per second per second. Or, in the case of a car, for example, you're interested in acceleration from 0 miles per hour to 60 miles per hour in a period of time that's measured in seconds. Okay? If your car takes hours to accelerate, then it's got some serious problems. So the units for acceleration here become a little weird. You have miles per hour, which is our velocity, per second, which is our time. Not the same unit, so they can't combine mathematically. And so we're left with miles per hour per second. So some weird units. And it's all because we're changing our velocity over a period of time instead of our position. And as long as we're on that subject, remember there's 3 ways to change your velocity. You can go faster, you can go slower, or you can change direction, like going in a curve. All of that will create an acceleration. Alright, free fall is when only gravity is acting on an object, so the free body diagram would be the force of gravity pointed down and nothing else whatsoever. Typically this is an idealization, meaning like a perfect world scenario, because there's usually a little bit of air resistance poking its head up here, but if we were to draw that free body diagram, that air resistance, here's our force of gravity, and if I were to draw the air resistance on this free body diagram, let's zoom out a little bit, it might look like this. So the point is, essentially, it's only gravity acting on it when we're talking about just dropping things on Earth. Things that are very heavy with very small surface. For example, dropping a person out of an airplane. Well, once they jump, let's assume they're parachuting and they haven't been pushed out of an airplane for some bizarre reason, then that person doesn't have much surface area, so they fall in essentially free fall and accelerate at a rate of 9.8 meters per second squared, which is actually the answer to the next question. But once they deploy the parachute, the surface area is increased, and their terminal velocity, how fast they can go, is decreased dramatically. And so once they deploy the parachute, they balance out that downwards pull of gravity with an upwards pull from the parachute. Which does not mean they go up. Instead, they fall at a constant velocity that is lower than it would be otherwise. That jerk that you would see when they're deploying the parachute and it seems like they're going up, that's an optical illusion. They're always going down. What in fact is happening is just the camera's perspective is changing very quickly. So it feels like it's being jerked up because there's a very sudden acceleration up, but it's to cancel out cancel out entirely the acceleration going down. So you still travel down, but you suddenly stop accelerating and start moving at a constant velocity. So that upwards jerk is actually an illusion. You're always falling down. At no point did gravity suddenly become anti-gravity. Alright, so acceleration of gravity, already said it in that last video or that last answer. is 9.8 meters per second squared, or 9.8 meters per second per second. And if we took the slope of a speed time graph or a velocity time graph, that is how we would get acceleration. Change in distance time is speed. Change in speed time, or technically velocity time, is acceleration. Okay. You could take the slope of a speed time graph, and yes, you would get acceleration. But it's better to do it from a position versus time graph. So again, it's one of those quirks of the graphs. They're going to say it's one thing when they're really talking about something that's very, very similar, but not quite the same. So let's move on to some calculations, some simple ones. Number 14 here, a train moves from rest, so 0, to a speed of 25 meters per second in 30 seconds. To find our change in velocity, in this case, it's simply a change in speed, so that's an acceptable distinction here. And we go from 25, or from 0 to 25. So we say 25 minus 0, and then we divide by 30 seconds. And 25 divided by 30 is 0.833. It looks like I did not write this one down, so let me do that real quick. 0.833, and our units would be meters per second divided by seconds, so meters per second squared. All right. Second one, a plane's average speed between two cities is 600 kilometers per hour. If the trip takes 2.5 hours, how far does the plane fly? Well, in this one, we look at our speed equation, distance over time. Distance is speed times time, if we rearrange this equation, times t times t. So distance is 600 times 2.5, which comes out to be 1,500. Again, it appears I forgot to write these down on this one. 1,500, and then our distance units are kilometers. Last example here, car traveling on a speed of 25 meters per second increases its speed to 30 meters per second in 10 seconds. What is the magnitude of acceleration? Final minus initial, so 30 minus 25 is 5, divided by 10 is 0.5 meters per second per second, or meters per second squared if you prefer. Okay, tune in for the next video for forces.